Bismillahirrahmanirrahim. Welcome to lecture number 10 for basic engineering mechanics. In this lecture, we would continue our discussion of equilibrium of a particle, and we would look at some more examples for 3D force systems, basically where we have a particle which is in equilibrium and which has forces acting on it on all three dimensions. So what were the basic procedure of analysis as we saw in last lecture? So first of all, we would like to draw a free body diagram of our particle, and then we would like to choose an appropriate axis to write our forces into their x and y and z components. We will label all the forces, which is basically a part of drawing a free body diagram. We would make sense of which force is positive in which direction also, and then we would write the equations of equilibrium. Here we would have three separate equations, one for sum of all the forces in x, and one for sum of all the forces in y, and one for sum of all the forces in z. And then we would solve for these equations. A few important points as we discussed last time: anytime we have a spring in our system, we know that the force in a spring is equal to the spring constant times the extension in the spring. And anytime a force comes out to be negative, that is the magnitude of the force comes out to be negative, then we would just understand that the force was actually being applied in the opposite direction. So let's continue and solve a few more examples. So here we have an example where we have a particle which has 5 forces acting on it. 2 of the forces are known. There is a 600 Newton force acting towards the x-axis. There is a 900 Newton force acting in the minus z-axis, and we have these 3 unknown forces. So the question is, determine the magnitude of the forces F1, F2 and F3 so that the particle is held in equilibrium. So first step again is to draw a free body diagram, and in this case the free body diagram is very similar to the picture itself, because we are only given a particle and the forces are already being drawn in terms of arrows. So we could simply say that this itself is the free body diagram. So let me just write that down. So this is the free body diagram for us. So just to save some time, we will not have to draw the free body diagram again. So the first step is already done, and the second step was to draw the 3 axes, and in this case we have already been given the x and the y and the z axis. So that part of the equation is that part of the problem has already been taken care of. So the next step is to write the equations of equilibrium. So the first equation of equilibrium is that sum of all the forces in x is equal to 0. This basically means that what are the forces that we have that have an x direction to them. So first of all, this force 600 Newton is in the positive x-axis, so we would have 600, and then this F2 is in the negative x-axis, so minus F2, and this F3 would have a positive component in the x-axis. But to find that component, first of all we would have to find this shadow, and then we would use that shadow to find the x component. So I can write that this is F3, and we have to do 4 by 3 to find the shadow, and then to find the x component I have to do another 3 by 5. So just to recap, this is the shadow of F3 on the xy plane. Okay, and so once we have the shadow and we then multiply by 3 by 5, this is 3, this is 5, and we use that to find our so that's the first equation. So we can now write the second equation, which basically is just sum of all the forces in y are equal to 0. And what are the forces which have a y component? First of all, these three forces, this 600 Newton does not have any component in the y-axis, this 900 Newton does not have any component in the y-axis, this F2 does not have any component in the y-axis. The only two forces which have non-zero y components is this force F1 and this force F3. So we would have F1 times 4/5, which is the y component of F1, minus F3 times 4/5 for the shadow, and then another 4/5 to find the y component. Again, we have a minus sign here because the y component of F3 is in the negative axis. So these are the two equations. The third equation is the sum of all the forces in Z is equal to 0, and the forces in Z is, first of all, we have this minus 900 Newton force which is in the Z axis. Then we have F1 has a non-zero component in the Z axis, and which is equal to plus F1 times 3/5. So this is also a component, non-zero component in the Z axis. And the third term is the F3 times 4/5. I just understood the connection, a fault that we made. So to find the shadow, we have to do 3/5 rather than 4/5. 4/5 would give us this vertical component, and 3/5 would give us the horizontal component. And to find the horizontal component, let me just make this correction here. So this is going to be 3/5, and this is also going to be 3/5. So now we have these three equations for and we have three unknowns. We have F1, F2, F3. So we can solve them simultaneously. So solve simultaneously. Okay. So these simultaneous equations are easier than they look. First of all, we can understand that these two equations only have two variables. So these only have F1 and F3 in them. So we can just solve them simultaneously without even caring about this third equation. And then we can plug in the value of F3, which we found from the first two equations, or I should call the last two equations, and plug that value in the first equation to find F2. So now we look at another example. So let me clarify that. So the in the second example, we have three cables which support a 40 kilogram flower pot, and we want to determine the force developed in each of the cables. Okay, so we have this cable D, AD, this other cable AC, and this third cable AB, and all of these three cables support this load of 40 kilogram, which is the load of the flower pot. So we want to find the force in each of these cables. So like last time, we start off by drawing a free body diagram of this center point particle. So we have a force in the y direction and the second force in the x direction. The third force has non-zero components in all of three axes, and then we have the flower pot, which is going to create a force which is vertically downwards. Okay, so all these are the forces. So let me just also label them. So this force we can just label as FB, and this force we can label as FC, and this one as, so the arrow should be at the end, so let me just fix that, and this is going to be FD, and the only known force is due to the flower pot, and which is going to be because the load is 40 kilograms, so we can say that there is a downward force of 400 newtons. Okay, and we would like to choose the same axes as have been chosen by shown in the diagram. So this is our y-axis, this is the, okay, so these are our axes. So this is the x-axis, this is the y-axis, and this is the z-axis. So this completes our free body diagram. Let me just label that free body diagram. Okay, and now the next step obviously is to write the equations of equilibrium. So we start off by writing sum of all the forces in x equals 0, and this is equal to so the only two forces which have a non-zero x component is this force Fc, which has a positive non-zero component in the x direction, and this force Fd. And to find the force, the x component of Fd, we would have to use the unit vector to find. So we know that this distance is 1.5, and we know that this distance is 2 meters, and we know that this third distance is again 1.5 meters. So this the length, so let me just say that the r vector, the position vector from A to D is nothing but minus 1.5 I hat minus 2 j hat and plus 1.5 k hat. So this is the position vector, and to find the force we need the unit vector of this position vector. So the x component would be of this force Ft would simply be equal to minus the x component of this force would be equal to minus Fd and times 1.5 divided by the square root of 1.5 squared times 2 plus 2 squared. So I just want to reiterate what I did here to make things clear. So this thing with the minus sign is just the x component of the unit vector of the position vector from A to D. And so we are just using the concept that we developed back in chapter number 2 about finding a force which is directed along a position vector. Okay, and so this is the component of the this is the component, and so the next step is to write the x component of the second force, which is simply, let me just revert back to the same color, and so that is equal to Fc. So the only two forces in the x direction is this force and the second force, Fc. So now we write the equations for the y. Sum of all the forces in y are equal to 0. What are the forces along the y axis? We have this force Fb, and the y component of this force Ft, which is going to be equal to minus Fd times 2 divided by square root of 1.5 squared times 2 plus 2 squared. And so this number comes out to be 2.9155. Okay, so this is just the magnitude of, this is basically the length of this rope from point A to point D. Okay, so this is our second equation, and so the third equation would simply be equal to sum of all the forces in Z are equal to 0, and so the two forces in the Z direction is Fd times 1.5 divided by this, again this magnitude, which is 2.9155, and then we have the second term, which is minus 400 equals 0. So equal 0 has already been mentioned, so we don't need to write that again. Okay, so now these are our three equations for equilibrium, and again these are very simple to solve. We can straightforward see that this equation only has one unknown, so we can use this equation number 3 to solve for Fd, and then we can plug in the value of Fd in the second equation and find the value of Fp, and then we can use the value of Fd again to find the value of Fc. So even though these are simultaneous equations, but we would never have to use the concepts of solving simultaneous equations for these equations. So let's look at another example. So let's get rid of all of this. So determine the magnitudes of F1, F2 and F3 for equilibrium of a particle. So again we have 5 forces which are acting on a particle, and we want to find the equilibrium, the magnitudes of F1, F2 and F3 such that this particle is in equilibrium. So this is very similar to the example that we did earlier, so I will not do here solve this example in the video lecture. We would solve this together in the class. Okay, so with this I want to just overview everything that we have covered in this chapter. First of all, we looked at the condition for equilibrium, and the only condition for equilibrium is that sum of all the forces on the system has to be equal to 0. So if we have multiple forces, then the sum of all of the forces has to be equal to 0, and this is the sum of the force itself, which is a vector. This is not the sum of the scalar of all the forces. So let me just clarify that this is a vector equation rather than being a scalar equation. So this is a vector F, and this is also, so the resultant force vector has to be equal to 0. Okay, so that was the first concept. Then we studied the equilibrium in 2 dimensions, and we saw that the only two conditions for equilibrium in 2 dimensions is that sum of all the forces in X has to be equal to 0 and sum of all the forces in Y has to be equal to 0. And moving on, we looked at the equilibrium in 3 dimensions and how that translates to 3 equations. Okay, So these were the basic concepts, and to add to these concepts, anytime we would have any pulleys, we would assume that those pulleys are ideal, and anytime we would have a spring, we would use the equation of a spring. And that is it for this lecture. I'll see you next time, inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.